Alright, in this video I will do many examples on point estimation. I hope to do about 10 of them. Okay, so examples on point estimation. Okay, let's start with the first example. Okay, suppose IID normally distributed with mean equal to mu and variance equal to sigma squared f. Now the question is to find bias and MSC of x bar, which is the sample mean, as an estimator of mu. Okay. Right. First, let's try to do the bias. So the bias of x bar, by definition, is the expectation of x bar minus mu, which is the expectation of minus mu. Taking the expectation inside, you get 1 over n times the sum of the expectation of xi minus mu. I'm sure all of you know that since xi has this distribution, the expectation of xi is equal to mu. So this is 1 over n times the sum of mu minus mu. So this is 1 over n. Sum of a constant is n times mu minus mu. So this is 0. So the bias is equal to 0, which implies that x bar is unbiased for mu. Right. The next thing we need to find is the MSC. Now, the MSC of x bar, using property 1, you should remember property 1 from the previous video. It says that MSC is the variance plus the square of the bias. Okay, but we just showed that the bias is 0, so this is equal to simply the variance of x bar. Okay, so this is the variance of 1 over n times the sum of xi. Now taking the variance inside the brackets, you get 1 over n squared times the sum of variance of xi. Right. Variance of xi, because each x has this distribution, the variance of xi is sigma squared. Okay. Okay, so this becomes 1 over n squared times n sigma squared, which is sigma squared by n. So this is your MSE, or the mean squared error, right? And as n approaches infinity, this goes to 0. Right? So this implies that x bar is consistent. For me. That's because the MSE, remember the definition of consistency, it says that an estimator is consistent if the limit of the MSE is 0 as n approaches infinity, which is the case here. So that's just example 1. Let's look at the second example. So this is example 2. Right, here you have a random sample from a uniform distribution with parameters theta and theta plus 1, and we want to find the bias and the MSE of the sample mean as an estimator for theta. Right, so let's start with the bias first. Taking the expectation inside, it becomes the expectation 1 over n times the sum of the expectation of xi. Now you may recall that for a uniform distribution, the formula for the expectation is a plus b divided by 2, which is, in this case, is theta plus 1 divided by 2. Okay. So this becomes 1 over n theta plus a half. Okay. So this is 1 over n times theta plus a half minus theta, which is theta plus a half minus theta, which is equal to half. Right? So the conclusion based on bias is that x bar is biased estimator of theta, right? In other words, it is not an unbiased estimator of theta, right? The next thing I'm going to do is I'm going to find the MSC of x bar, right? You may recall one of the properties I proved is this: the MSC is equal to variance plus the square of the bias. So using this, using this property, you can write this as variance of x bar plus bias is half squared. If you take the variance inside, it becomes 1 over n squared sum of the variance of xi plus a quarter. Now you may recall the formula for the variance of a uniform distribution is b minus a squared divided by 12. So in this case, your b is theta plus 1 minus a is theta. Alright. Okay, so that is 1 over n squared times n times 1 divided by 12 plus a quarter. So this is n divided by 12 times, sorry, not n, plus a quarter, right? N divided by 12 n squared, which is 1 divided by 12 n plus a quarter. And this, as n approaches infinity, this goes to quarter. Okay, so hence x bar is not a consistent estimator of theta, right? Okay, so in this example, the x bar is a biased estimator, which is not a good thing, and it's also not a consistent estimator, which is also not a good thing, right? Okay. Remember, a good estimator is one which is unbiased and which is consistent. Example 3. Is the following. Suppose a variable x has a binomial distribution with parameters n and p. Find bias right? Find the bias of x divided by n as an estimator of p, right? So it shouldn't be too difficult. So let's Okay. So this implies that x divided by n is unbiased for P. Right, so that completes example 3. Example 4. I suppose you have a random sample from a Poisson distribution with parameter lambda, and the question is to find bias and MSC of x bar, the sample mean, as an estimator of lambda. Right. Okay. So let's start with the bias first. Take the expectation inside, you get this. Now all of you know that the expectation of a Poisson variable is lambda, so this is 1 over n times the sum of lambda minus lambda. So this is 1 over n times n lambda minus lambda, which is 0. Alright, so what this means is that x bar okay. Alright, next to find the MSC, I'm going to use property 1, which says this, so this is 0, so this becomes the variance of x bar plus 0, which is the variance of this. Taking the variance inside the brackets, you have 1 over n squared right. Now the variance of a Poisson variable is lambda, so this is 1 over n squared times the sum of lambda, so this is 1 over n squared times n lambda, which is lambda by n, and which approaches 0 as n goes to infinity. Alright, so this implies that x bar is consistent for lambda. Right, so this completes example 4. Yeah, and the next example I'm going to look at is slightly different. This is example 5. Suppose you have two data points, say x1, x2. Right. So the question here is to find the bias of this as an estimator of that. Right. Okay, let's see. I mean, this question is slightly different to the previous ones. So let me show you how to do it. Okay, this is the definition of bias. Now to find the expectation of this, you can't just take the expectation inside. That's not allowed. Alright? So what you need to do is, the first thing you need to do is to find the distribution of the maximum of x1 and x2. So that's what I'm going to do. So I'm going to let Z denote the max of x1, x2. Right? Then the CDF of Z is as follows. Okay, and this is the same as saying if the maximum is less than or equal to Z, then each of these guys has to be less than or equal to. So this is the probability that okay. Now because x1 and x2 are independent random variables, you can write this as okay, that's by independence. Right? Now, x1 we know is a uniform variable, x2 is also uniform. So what you have here is the CDF of a uniform, theta, theta plus 1, theta, comma, theta plus 1, and the same thing here. So I'm sure you guys know the CDF of a uniform is Z minus A divided by B minus A. So it's Z minus your A is theta, B minus A is theta plus 1 minus theta. Okay, so this is Z minus theta squared. So this is the CDF, and the PDF is just simply the derivative of this with respect to z. So that will be 2 times z minus theta. So let me put this in a box so that you don't get lost by what I have done here. So this box here, what I have done is to derive the CDF and the PDF of the max of x1 comma x2, which I called z here. Right. All right. Now let's continue from over here. Right. So this is going to be equal to the expected value of z minus theta. Now, to find the expectation, I'm sure you guys know, you just need to integrate z times the PDF, which is 2 times z minus theta, and the limits of integration are from theta to theta plus 1, because that's the limits of the uniform distribution. Right. Now, the integration is pretty straightforward, so you can take the 2 outside. Z squared, the integral of that is z cubed divided by 3 minus theta z, so it's going to be theta z squared divided by 2. Then you take the limits from theta to theta plus 1 minus theta. Okay. Now, the limit at theta plus 1 is right, and the limit at theta is this, and clearly you should work this out, right? Clearly this is not equal to 0. So, right? So the conclusion is that the estimator max of is a biased estimator of theta. Right? In other words, it is not an unbiased estimator. Right? So that completes example 5. Next, example 6. Suppose IID, when normally distributed, 0 mean and variance sigma squared. In this example, the question is to find the bias and MSC of the following. This is the sample variance with dividing by n minus 1 instead of n. So this is known as the unbiased sample variance. As an estimator of sigma squared. Right? So the first thing I want to do is to find the bias of the estimator. So this, as you know, is the expected by definition, is the expectation of the estimator minus the parameter that you're estimating. Okay. So this is the expectation of right. Okay, I'm going to pull out the n minus 1, which is a constant outside the expectation. Right, and also I'm going to multiply by sigma squared. You see why I'm doing this in a minute. And because I have multiplied by sigma squared, I need to divide by the same. Okay. All right. Now, you may recall this expression from the video I did on chi-square distribution. One of the properties I gave you in that video is that this expression here has the chi-square distribution with n minus 1 degree of freedom. So it's using property of chi-squared. Okay. Right. Another property I mentioned in that video is that the expectation of a chi-squared variable is equal to the degree of freedom. So this guy here is equal to n minus 1. Right? So these two cancel out, you get sigma squared minus sigma squared, which is 0. Right? So the conclusion here is that S squared is an unbiased estimator of sigma squared. Right? And this is exactly, the keyword here is unbiased. This is exactly what I meant when I said that dividing by n minus 1 gives you an unbiased sample variance. What I meant by that is that the bias of it is equal to 0. Right? So S squared is an unbiased estimator of sigma squared. The next thing I want to find is the MSC of S squared, which is by one of the properties I gave you in the last video is equal to this. But we know that the bias is 0, so this is the same as the variance of S squared plus 0, and this is equal to the variance of Now I'm going to pull this constant outside. So remember, when you pull a constant outside the variance, it becomes 1 over n minus 1 squared times the variance of Alright, the next thing I'm going to do is I'm going to multiply this by sigma power 4, right? And because I have done this, I need to introduce something corresponding here, which will be 1 over sigma squared, right? Because when you take the sigma squared outside, it becomes sigma power 4. All right. Now, using the same property I mentioned in the previous slide, what you have here, this expression here has a chi-square distribution with n-1 degree of freedom. So once again I'm using the property of a chi-squared variable. So if you don't remember this, I suggest you look at the video on chi-squared distribution. Now another property I mentioned in that video is that the variance of a chi-squared is equal to 2 times the degree of freedom. So it's 2 times n-1. Okay, so this becomes 2 sigma power 4 divided by n-1. And this clearly approaches 0 as n approaches infinity. So the conclusion here is that a squared is a consistent estimator of sigma squared. So it is an unbiased estimator, and it's also a consistent estimator. So it has both good properties. Right, so that's your example 6. The next example, 7. Right, suppose you have a random sample from a normal distribution, 0 mean and variance sigma squared. Now in this example I'm going to find the bias and MSC of the following. As an estimator of sigma squared. So let's start with the bias first. So the bias of by definition is the expectation minus the parameter. Alright. Now I'm going to do something here. I'm going to take the 1 over n outside, which is a constant, and write it like this. Right. Now I'm going to multiply this by sigma squared. Because I have multiplied by sigma squared, I need to divide. Alright, so I'm doing this. Now, if you look at the video on chi-square distribution, one of the properties I gave you is that anything of this kind, when xi have this distribution, this expression must have a chi-square distribution with n degree of freedom. So this once again using property of chi-squared n. So I suggest you look at the video. If you don't remember this, please look at the video on chi-square distribution, right? Okay, in the next step, I'm going to use the fact that the expected value of a chi-squared is the degree of freedom, which is n here. So this is sigma squared minus sigma squared, which is 0. Right, so this proves, so what we have shown here is that is an unbiased estimator of sigma squared. Okay? Alright, the next thing, I want to find the MSC, right? So the MSC of MSC of this is equal to the variance using the property on point estimation is the variance plus the square of the bias. Now, obviously, the bias is 0, so this is simply the variance of 1 over n plus 0. Right now, as in with the bias, I'm going to take the 1 over n outside the bracket, so it becomes 1 over n squared times the variance of the sum of xi squared. Right. Now I'm going to multiply this guy here by sigma power 4. So I need to reciprocate. So to reciprocate sigma to the power 4, I need to divide by sigma squared. Okay? You see, when you take the sigma squared outside, it becomes sigma power 4, so which cancels with this one. So this is sigma power 4 divided by n squared times the variance of this. Now, using the property of chi-squared, which I used, the same property I used with the bias calculations, what you have here has a chi-square distribution with n degree of freedom. Right, so it's using Now, I mentioned earlier that the variance of a chi-squared variable is 2 times the degree of freedom. So this is 2 times n. So this is equal to 2 sigma power 4 divided by n. And this approaches 0 as n approaches infinity. Right, so the conclusion here is that this estimator is consistent for sigma squared. Alright, so once again this estimator has both the good properties, that is, it is unbiased for sigma squared and is also consistent for sigma squared. Right? So that completes example 7. Now example 8 is slightly different. Now let you have suppose you have 2 independent binomial random variables, the one with parameter m and p, the other one with parameters n and p. Consider the following estimators. So the first estimator is p1 hat equal to half divided by x divided by m plus y divided by n. And the second estimator for p is p2 hat is x plus y divided by m plus n. Now the question is, which of the estimator is better? Which one is better and why? You will get a question like this in the exam. So to decide which of the estimators is better, you need to compute the biases of the 2 estimators, and also you need to compute the MSCs of the 2 estimators. And then from the calculations you should be able to judge which of the 2 estimators is better. Right? So let's first compute the bias. So starting with the bias of the first estimator, which is the expectation of both these estimators for P. So this is the expectation of minus P. Right, taking the expectation inside, you have half times 1 over m times the expectation of x plus 1 over n times the expectation of y. Okay. Now, I'm sure all of you know the formula for the expectation of a binomial variable. Right, since x has this distribution, the expectation is n times p, and similarly the expectation of y is n times p. Right? So what you get is p minus p, which is 0. So the bias of the first estimator is 0. Now let's see what happens to the bias of the second. right? This is the expected value of x plus y okay. Now taking the expectation inside, we get the expectation of x is m times p, and the expectation of y is n times p. So once again you have p minus p, which is 0. So the conclusion that you can make in terms of bias is the following, that both p1 hat and p2 hat are equally good with respect to bias. Right? So that's the conclusion you can make with respect to bias. So the next thing we need to do is to find the MSC of the two estimators. Right? So that's what I'm going to do now. Is to find, let's find the MSC of P1 hat first. So this is the variance of P1 hat plus the square of the bias of P1 hat. We know that the bias is 0, so this is simply variance of P1 hat plus 0. Alright, so this will be the variance of P1 hat is half of x divided by m plus y divided by n. Now, taking the variance inside, you have to be careful when you pull the constants, you need to square them. So this becomes 1 over 4 in brackets 1 over n squared times the variance of x plus 1 over n squared times the variance of y. Okay, so this is quarter 1 over n squared. The variance of x, I'm sure all of you know, is mp times 1 minus p, and the variance of y is np times 1 minus p. Alright, so this becomes a quarter 1 over m Alright, so this is the mean square error of the first estimator. Right? Let me call this equation 1. I will need it later on. Okay. Now let's find the MSC of the second estimator. Once again, the bias is 0, so this is the variance of P2 hat plus 0. So this is the variance of x plus y divided by m plus n. Now pulling the constant outside and bringing the variance inside, we get Now variance of x, I'm sure that you know, is m p times 1 minus p, and variance of y is m p times 1 minus p. Now simplifying this, you get the following. You get 1, or you get p times 1 minus p divided by m plus n. Now let me call this equation 2. Now, so this is the MSE for the first estimator, this is the MSE for the second estimator. Remember that the estimator that has a smaller MSE is the better one. So you need to decide between these two, which one is smaller, right? So the question is, which one is smaller? So I'm going to answer that in a sec. Now, suppose, I'm just guessing, I may be wrong, right? Suppose 2 is the MSE for the second estimator is less than or equal to the MSE of the first estimator, right? So that's the same as saying that right? Alright, now let's try to simplify this. These two guys cancel. This one here cancels with this one. Alright, and so this becomes 1 divided by m plus n less than or equal to quarter m plus n, right? And this is the same as saying that, let's bring this here and bring this 4mn is less than or equal to m plus n squared, right? Let me take this away and bring it over here. Now it should expand the right hand side. You have 4mn less than or equal to m squared plus n squared plus 2mn. Alright? So that's the same as saying that 0 is less than or equal to m squared plus n squared minus 2mn. And this is the same as saying that 0 is less than or equal to, you can factor this as this, right? Which is right, which is always true because anything squared has to be non-negative, right? So what this means is that the second estimator has a smaller MSE than the first estimator. So hence the question is hence right, so we prefer P2 hat to P1 hat, right? Okay, remember you choose the estimator that has the smaller MSE, right? In this case, P2 hat has the smaller MSE, right? Okay, so this completes example 8. Next example 9, right? right? You have three observations from a normal IID, from a normal distribution with these parameters. Consider the following estimators. So we have two estimators once again. The first one, both of them are estimators for mu. The first one is this one, right? And the second one is right. So the question is the same: which is better? Which one is better, and why? Okay. So to do this kind of question, once again, you need to find the biases of the two estimators, and also you need to find the MSCs of the two estimators, right? So let's start with finding the biases. So the bias of this, right? So this will be minus mu. Yeah. Taking the expectation inside, you have quarter minus mu, right? And each of these is equal to mu because we are assuming is a IID normal with these parameters. So this will be a quarter mu plus 2 mu plus mu minus mu, which is equal to mu minus mu. So it's equal to 0. So the bias of the first estimator is 0, which is a good thing. Right? Now let's find the bias of the second estimator. So this is going to be okay. And taking the expectation inside, you get a third times the expectation of x1 plus the expectation of x2 plus the expectation of x3 minus mu, right? So this would be a third times mu plus mu plus mu minus mu. Alright, so this is mu minus mu, which is 0. So both estimators, mu1 hat and mu2 hat, both of them have biases equal to 0. So the conclusion in terms of biases is the following: they both smooth estimators are equally good with respect to bias, right? So the next thing we need to do is to find the MSCs of the two estimators. So that's what I'm going to do here, right? So starting with the MSC of the first estimator, which is the variance plus the square of the bias so this is the variance plus 0, right? Okay, so this is going to be the variance of this, right? Taking the variance inside, you should remember to square the constants. So this is going to be 1 over 16 times the variance of x1 okay. This is what you have. Now we know that the variance of each variable is sigma squared, right? So this is going to be 1 over 16 sigma squared plus 4 sigma squared plus sigma squared, right? So this is going to be 3 sigma squared divided by 8. So that's the MSC of the first estimator. Right now, let's also find the MSC of the second estimator. We know that this is 0, so this is going to be the variance of mu2 hat plus 0. So this is the variance of divided by 3. Right? Now taking the variance inside, remembering to square the constants, you get 1 over 9 in brackets variance of x2 plus the variance of x3. Alright? Now each of these guys is equal to sigma squared, so it's 1 over 9 sigma squared plus sigma squared. Right, so this is sigma squared divided by 3. Right, let me call this once again equation 1. Let me call this equation 2. Now the question is, which of them is smaller, right? Whether it's equation 2 smaller or equation 1 is smaller. Clearly 2 is smaller than 1. Right. Okay, which implies that MSC of the second estimator is less than the MSC of the first estimator. So this implies that we should choose the second estimator over the first estimator. Alright, so this completes example 9. The final example is a little bit involved. I mean, it's more advanced than. It's not more advanced. It's just more calculations than the other examples I have done. So I will just do this as the final example. But if you'd like me to do more examples than the 10 examples I have done, please let me know. Okay. Suppose IID with the CDF given by the following formula: f of x equal to 1 minus e theta minus x, where x is greater than theta. Let Right, so we have an estimate for theta, which is the minimum of the data, and we want to find the bias and the MSC of theta hat. Now remember, I did a similar question earlier where you had 2 data points and the estimator involved the maximum. When you have a minimum or maximum, the first thing you must do is to try to find the distribution of that minimum or the maximum, right? So that's what I'm going to do here. The first thing, before finding the bias or the MSC, you should try to find the distribution of the minimum or the maximum, right? So that's what I'm going to do first thing, right? So let, just for the sake of notation, let Z denote the minimum of x1 to xn. Okay, then the CDF of Z, right, is as follows, which is the probability that capital Z less than equal to little z, right? And I'm going to write this, you see why I'm doing this, I'm going to write this as the probability that capital Z is greater than little z, right? And this is 1 minus the probability that the minimum is greater than little z, yeah? Now, if the minimum is greater than a fixed number, that is the smallest value of n data points, if that is greater than a fixed number, that means that each data value must be greater. I hope you follow what I'm saying. So this is the same as saying that x1 is greater than little z up to xn is greater than little z. Okay. Now, because x1 to xn are independent random variables, so using independence of x1 to xn, we can write this as okay, and also because x1 to xn are identical. Remember, we are saying IID, which means independent and identical, right? So because of that, each of the probabilities here is the same. So you can write this as the power n, right? Alright, now I'm gonna write this as 1 minus the probability that x is less than or equal to z to the power n. Now this is your f, the CDF f, right? So this is simple 1 minus capital F at z power n, right? Which is given as equal to this. So subbing that in, you have 1 minus 1 plus e theta minus z power n. Alright. So you have 1 minus e n theta minus n z. So this is the CDF, or the cumulative distribution function of the statistic minimum, right? So the PDF of z is just simply the derivative of this with respect to z, alright? So you differentiate the CDF. So if you do that, you get n e n theta minus n z. Alright, so this is the first step you must do for whenever you have a question that involves the minimum or the maximum. You must do this step, that is to find the CDF and the PDF of the statistic which involves the minimum or the maximum. So let me put this just to highlight what I have done. Now, let me put this in the box, okay? Okay, so we have found the CDF of z and the PDF of z. Alright, now we can return to the question, which is to find the bias and the MSC of theta hat, right? So let's start with the bias. Alright, which is the bias of z, right? Which by definition is the expectation of z minus theta, right? Because remember, theta hat is an estimator for theta. So this is the definition, right? Right. To find the expectation of z, you just need to integrate this with respect to z, right? So it's gonna be the integral of z times n times e to the power n theta minus n z dz, and the limits of integration is from theta to infinity. That's because the limits of integration are from theta to infinity is because of this condition here. It says x is strictly greater than theta, which also means that the minimum has to be strictly greater than theta. So the smallest possible value for z must be theta, and the largest possible value is infinity. Right, so let's return to over here. Okay. So what you have is pulling out the constants. You have to the integral from theta to infinity of z. Okay. All right, now to do this integration, there are several ways you can do this integration. one way is to use integration by parts. I'm sure you know integration by parts. You must have done this long time ago. So using integration by parts, this is what you will get. Right? Minus theta, right? This is what you get, okay? Let me take this away. So, now let's simplify this. And, right, the limit at infinity is 0, and the limit at theta is the following. Okay. Then you have to integrate this, which is not difficult. And take the limits from theta to infinity. Then minus theta, of course, don't forget. Right? Then you have n, e and theta. Right, now the limit at infinity is 0. The limit at theta gives you this. Okay, minus theta. Okay, right, now let's simplify a little bit. So this becomes n, e and theta in brackets, theta then plus okay. So this is I hope you follow me so far. So this is theta plus 1 over n minus theta. So which is equal to 1 over n. So what we have shown so far is that the bias of theta hat is equal to 1 over n. So it is. So this implies that theta hat is a biased estimator. However, right, theta hat is asymptotically unbiased. It's asymptotically unbiased since the limit of the bias as n goes to infinity is equal to 0. Remember, if you take the limit of this as n approaches infinity, you get 0. Right? Okay. So that's the first part of the question. Now the second part is to find the mean squared error, right? So that's what I'm going to do. I'm going to do next, right? Is to find the MSC of theta hat, which, as you know, is the variance of theta hat plus the square of the bias. Right? So this is the variance of Z, right? Remember we called theta hat equal to Z earlier, plus this is the bias, you may recall, is 1 over n squared. Now the variance of Z, you can write it as the expectation of Z squared minus the square of the expectation. Okay. Right, now we know that we already know what the expectation of Z is, right? From what we did earlier, right? So all we need to find is the expectation of Z power 2, right? So to find this, you integrate from theta to infinity of Z squared times the density function, which is this. And from what we did earlier, the expectation of Z is theta plus 1 over n squared plus 1 over n squared. Right? Okay, guys. Right. Now I'm going to put the constant outside, so this is going to be n integral from theta to infinity of Z squared e minus nz dz 1 minus okay. Right. Next thing, to find this, I need to apply integration by parts. Okay, right? So don't be scared. I know you must have done integration by parts many times. So you shouldn't be afraid. Okay, so let's apply to this. Right? So you should do integration by parts. This is what you would get. Now taking the limits, let's see what we get. So this the limit at infinity will be 0, right? And the limit at theta will be minus, so it gives you plus theta squared. Yeah. And this integral here, to do this, we need to apply integration by parts one more time. But we have already applied, as part of finding the bias, we found this integral by integration by parts. So I'm not going to do that again. I just want to copy what I did in the bias part and from what we did in the bias part, we know that this guy here is equal to the following. Alright. Okay, so close bracket, and then I know it looks like a clumsy expression, but you will see in a minute it produces quite a bit, right? So if you multiply everything within the brackets by this, this is what you will get. You get theta squared plus 2 theta by n, so theta by n plus 1 over n squared. And then you have these two terms which are okay. Now if you simplify this, which is not difficult, you will get 2 divided by n squared. So your MSC, after all, is very simple. It's 2 divided by n squared. So this implies that your MSC of theta hat is equal to 2 by n squared. Right? And clearly this approaches 0 as n approaches infinity. Right? So theta hat is a consistent estimator of theta. All right. So this is it's not a difficult, but it's a lot of calculations in this example. But apart from that, it's not so difficult. So in this example, we have shown that the theta hat is a biased estimator, but it is asymptotically unbiased. But a good thing is that it is also a consistent estimator of theta. Alright, so this completes the 10th example. If you like me to do more examples, please let me know. But for the time being, this is the end of this video. And in the next video, I will talk about a method for constructing estimators known as the method of maximum likelihood, right? Or MLE for short.